Why, how you doing there, good looking? We are back for part 2 of the review notes for Unit 6, Differential Equations and Math Modeling. This is an AP Calculus AB review course. We are reviewing all of Unit 6. We are not just doing Unit 6 Day 1, Unit 6 Day 2, etc. We're covering all the important stuff, so it's not every single bit. You should have seen most of this stuff by now, so let's continue where we left off from part 1, which I believe was integration U sub with bounds. And that is right where we left off. Okay, definite integrals with U sub. Definite means we now have bounds here. This is fantastic. It's fantastic, children. Get me some coffee right now. So, if we can kind of review what we did in this part 1 video with determining which function should be my U function with U sub. All right, and we always use the highlighters, which are a fan favorite of Mr. Visca's. But I'm looking at this equation here, the integration from 0 to pi over 4 of tan of x secant squared of x dx. Now, what I said in determining which one is my U and which one is the derivative, which means you're going to see a function and you're going to see, if not all, part of the derivative of that U function. In this case, it becomes easy, all right? Meaning, I'm going to make U tangent of x because I know the derivative of tangent is secant squared of x, okay? And then I always slap on a dx there. So let's make U tan of x. Du, the derivative of U, is secant squared of x dx. That is perfect. It is going to substitute in very nicely. So I'm going to draw my little integral. I'm not going to put my bounds yet. Okay? In for tangent of x, I'm going to put a U. Right? In for secant squared x dx, I'm going to put du because that's what it is. Now, you must U sub your bounds, okay? Upper bound, lower bound, okay? They are currently in X form. We want them in U form, all right? Meaning, if I know what X is, I'm just going to substitute in that X upper bound. So, for my upper bound, I'm going to call that UB. It's the tan of whatever that upper bound is. It's pi over 4. You should know that's 45 degrees, and the tangent of 45 degrees is 1. So my new upper bound, when x is pi over 4, is 1. All right? And now I've got to do the same thing for my lower bound. I'll call that LB. I'm taking the tan of x. In this case, my x value is 0. And the tan of 0 is 0. So, now, why is this good to do? Could I have done this U sub without changing the bounds and then put my tan of x back in for U and then done my bounds? I could have. However, on the AP exam, and I've said this before, on the AP exam, they will give you an equation. They'll give you an equation like this. And they will literally tell you, okay, if I use tan of x for U sub, what will my integration look like? Not what will the answer look like, what will the integration look like? And it'll be multiple choice. One of them will look just like this, what we wrote here. And one of them will look like this, except the bounds will still be in x form, okay? The correct answer is this one right here. Okay, so you need to get used to doing your U sub on your bounds before you integrate. All right, do not do it like this. Number one, it's easier this way. It's easier this way. When I change it to, I mean, look at how much easier is it to integrate with a 1 than pi over 4? I mean, come on. All right, so let's begin our integration. All right, let's do this nice. Remember, I'm going to add 1 to the exponent and then divide by that. So it's U squared over 2. I do not have to put plus C. How come I don't have to put plus c? Because I have bounds. There is no expression in my answer. It is actually going to be a value. Okay, hopefully a number. And I want that from 1 to 0. And how do I integrate? Simple. I put the top bound in first for u. Okay, these are u's now, so we can go right in here. So it's 1 squared over 2. Whatever value that is when I put the first or upper bound in, I subtract, then putting the lower bound in for my u. 0 squared over 2. Love throwing in zeros because this goes bye-bye, it just becomes 0. 1 squared is 1. It's 1/2 minus 0, which is 1/2. That was a million times easier to integrate than trying to throw in pi over 4 and 0 into tan x, secant squared x, whatever we would have had to do. Million times easier. Million times easier. Now, let's take a look at our second example. There we are. Now, what, pray tell, what do I make u and what do I make du? All right, well, I'm going to say, here's my u, and whatever I make u, I should see some or all of the derivative of that, and that's going to be where I start. So I am going to make u x cubed plus 1. Why am I going to make that x cubed plus 1? Because the derivative of x cubed is 3x squared, and then I always need to slap on that d. It's a dx. It will be a du. All right. So, and look at, that's going to substitute completely. I don't have to, get any number from the right side of my equation here over to the left side. I don't, because this is present in its entirety. All right. So let's substitute that in. So I have an integration. I'm not going to do my bounds yet. Okay. U is going in for this part right here. So instead of x cubed plus 1, it's the square root of u. Okay. These two get taken out and become du. Now I should change my bounds. My upper bound is 1. These are x equals 1. And my lower bound, x is negative 1. So I'm going to put 1 and negative 1 in for this x. And it's going to give me the new upper and lower bounds in u form. Okay, so my upper bound, I put a 1 in for this x. So it's 1 cubed plus 1. That's going to give me 2. That is my new upper bound. Bam! My lower bound, I'm going to put a negative 1 in. Okay, so it's negative 1 cubed plus 1. That's negative, that's 0. Nice, 0. There you go. That right there is a million times easier to integrate than what we started with here. Okay, that would have been kind of disastrous. So now, because I know derivatives and integrations are so much easier when we have exponents, I am going to change, all right? I'm going to change this square root to a power of 1/2. So basically I have the integration from 2 to 0 of u to the 1/2 du. Okay, so I add 1 to this exponent, u to the 3/2, okay, and I divide by 3/2. Dividing by 3/2, or dividing by any fraction, is the same thing as multiplying by its reciprocal, in this case, 2/3, all right, and I want that from 2 to 0, okay? So let's take a look at what we got here. Let's take a look at what we got here. Love using zeros, my fave. But I'm going to first put a 2 in for u here. So I've got 2 to the 3/2 all over 3. This is what happens when I put a 2 in. Minus putting a 0 in. 2 times 0 to the 3/2 over 3. I know this is going to go bye-bye to 0. Extendo. Now, I've got to cube 2 first, then take the square root of it. So I've got 2 times 2 cubed is 8. I've got to take the square root of it, all over 3. All right, so ultimately, 2 times the square root of 8 over 3 minus 0 is 2 times the square root of 8 over 3. However, if I had so wanted, I could simplify this, all right? Algebra, algebra, algebra. I tell my calculus kids that calculus is so full of algebra that it's crazy. If you understand the concepts and setting up the equations and processes, 85% of it is algebra, all right? So if this were multiple choice, 2, the square root of 8 is the same thing as saying the square root of 4 times the square root of 2, which is 2 radical 2 over 3. And now I can multiply 2 times 2 here and get 4 radical 2 over 3. If this were multiple choice, it would probably look like this. If it were short answer, hey, fantastic, like that. Unless they tell you you need to simplify, okay? So we are good to go. Good. Seems quite painless so far. Separable differential equations. Okay, these are kind of like implicit differentiation. Remember back in the day, was it Unit 3 or Unit 4 review? We had derivatives that we could not get our y equals alone. We called it implicit differentiation. Okay, if I had x squared plus xy plus y squared equals 8, I couldn't get y equals, so I can't just take the derivative of an equation, correct? So I had to take the derivative of x and the derivative of y. And every time I took the derivative of y term, I would always have to put dy dx next to it. But we knew we had to do that. We knew we had to do that process when we couldn't get y alone. Same thing here. Okay, I can't take just the integration of y equals something and just integrate the right side of my equation and get an answer, because I don't have just y equals by itself. I have y squared, all right? Also, most of the time, they will tell you on the AP exam, here's a separable differential equation, integrate it. They will use the words, all right? 99% of the time, they will do just that. So what do I need to do here? All right, well, we're integrating this. Okay, we got to integrate this. Please note that when we integrate, notice one thing. We always need to have our dummy variable, right? I'm going to integrate this, need a dummy variable. I'm going to integrate this, I have my dummy variable. When I'm integrating this, look what happens. I have x, and then I have a dummy variable dx. I also have a y variable, and I have a dummy variable for y. So I am going to isolate my y variable with my dy, my dummy variable for y, and my x variable with my dummy variable for x, which is dx. So let me do just that right now. What I will do is I will multiply this side by dx, and I will do this one step at a time. I could do it multiple steps at once. So this goes bye-bye, and I have dy equals 2xy squared dx. Now, I want to get rid of that y squared because it does not belong. I have 2x dx, which is good, but the y squared, no, not so much. So I'm going to divide this by y squared. I'm going to divide this by y squared, okay? This goes bye-bye, all right? So look what I'm left with. Okay, keep in mind this is 1 in front of the dy, right? So I'm going to say I have 1 over y squared dy equals 2x dx. Separable differential equations. I have separated the two differential equations I have. I have a differential equation with y on the left side, and I have a differential equation with x on the right side. So now all I'm going to do is just integrate both. That is it, okay? Once I split these up, I can integrate, because when I integrate, remember, when the integration goes bye-bye, so does the dummy variable, right? When the integration goes bye-bye, so does the dummy variable. That's what we're going to do right here, right now. Right here, right now, right here, right now. But the first thing I'm going to do is I'm going to change this on the left. I'm going to bring this up and negate my exponent because it's always easier to work with exponents if I can avoid the fractions. Okay, 2x dx. Now I'm going to integrate. All right? Bam. Now, don't forget, I'm going to add 1. That'll become y to the negative 1, and then divide by negative 1. Okay, simple. I divide by that new exponent. This is 1. I'm going to add 1. This becomes 2. So it's 2x squared over 2. These cancel. And I end up with, okay, negative y to the negative 1 equals x squared. And before I write that equals x squared, did I have bounds? Do I have bounds at all? Did I have bounds here or here? No. Did I have bounds here or here? No. When I don't have bounds, I always need a plus c. Okay, I could have put plus c here and plus c here, but I wanted to worry about simplifying our equations first, all right? So, this is what we got. Ready? I hope so. Now, what do I do here, okay? First of all, I'm going to solve this. I need my answer in the form y equal. Okay, so let me say that again. I want my answer as y equals. So I want to try and get the y alone, all right? So first of all, I've got to subtract c from this side and subtract c from this side. This is what I don't want you to get in the habit of. Just because this equation is a constant and this equation is a constant doesn't mean they're the same constant. So some people like to put C1 and C2. So if I'm subtracting C1 from both of these, yes, these will go bye-bye. This doesn't go away. I mean, maybe they're the same constant, but not always, okay? So if I have one constant, 7, and I subtract another constant, 3, I still get another constant, don't I? This is what the mentality is going to be over here. I have negative y to the negative 1 equals x squared, still plus some constant. But mister, what if this was a negative and this was a positive? I'd have negative 4. Negative 4 is still a constant. I can still add a negative 4, can't I? I can, okay? So that takes care of our C dilemma. I don't have my kids write the 1 and the 2 here, okay? Some people do, but they dang well better know that when I cancel this one still stays, okay? Some people need to see that 1 and 2, and that's fine. You just better understand that concept, okay? So let's solve for y here on this side. Let us multiply both sides by negative 1. Multiply this whole thing by negative 1. Multiply this whole thing by negative 1. So now my negatives cancel, and I just get y to the negative 1 equals negative x squared, still plus c. All right? So far, so good. Now, okay, I want this y alone, so I want to get rid of the negative 1. So I'm just going to flip the fraction again, because technically this is over 1, right? Equals negative x squared plus c. Now, here's a rule that a lot of people forget because we don't really use it too much. If I flip this, if I call this y over 1, which is just y, I can just flip these two. And that's your answer. That's your solution right there. Okay. Y would equal, it's a fraction, 1 over negative x squared plus c, or you can, I mean, sometimes they'll pull that negative out front. It might be 1 over x squared plus c, negation, whatever. It doesn't matter. In this case, because the constant is still going to be plus a c. Bam. There you go. Nice. I like it. I like it a lot. Now, I went over a lot here. I mean, kind of yes, kind of no, but it's, again, very algebra heavy. As soon as I get to this point here, okay, as soon as I separate these, and I have two separable differential equations where I can integrate them both, okay, then it just becomes all algebra, okay? And I did everything, I did every single step on the right-hand side. If I was doing this without instructing, I would have combined some steps, and it wouldn't have been quite as much. But I wanted to show it to you again so that you see it all. All right, how are we doing? 19-minute mark, perfect. Last one. All right? This one looks a little bit complicated, but if you know your rules, this is actually really, really easy. Okay? So I see I have a dy, a dx on the left. I have an x and a y variable on the right. This just screams separable differential equations. All right? So I'm going to get my dx and all my x terms on the right side, and my dy and all my y terms on the left side. So first thing I'm going to do, I'm going to multiply this side by dx and multiply this side by dx. This will go bye-bye. Okay? Then on the right side, oh, I should really write it out. I like combining steps. 2x times 1 plus y squared e to the x squared dx. I want to get my 1 plus y squared term from the right side to the left. Okay? Now remember, this is still a 1 up here. Okay, so when everything's all said and done, I've got 1 over 1 plus y squared dy equals 2x e to the x squared dx. Now, I'm going to integrate both sides. Now, I said you should know your rules, correct? I think I did. So, in fact, combine, perfect. Make this bigger here. This is what we got to work with. Okay? This is what we got to work with. First of all, I'm looking on the left side thinking like, how do you do this? How do you do this? If you remember your trig rules, the derivative of what equals 1 over 1 plus y squared, all these y's, the derivative of the inverse of tan. Okay, the derivative inverse of tan. So if I'm going backward, boom, this is a rule. There is no algebra you need to do here. It is knowing the rule tan negative 1 of y, and we do not have bounds, so we always put our plus c. If you know your rules, it's easy. Okay? Second thing here. Ew. Guess what? I'm going to do u sub. This is a great problem. Not only does it involve trig, specifically inverse of trig, know your rules, we're working on separation of differential equations, and on top of that, we need to do u sub. It's a really great problem. Okay? How do I know I got to do u sub? Because I see, not only do I see a function, x squared, I see its derivative in there. So I'm going to let u equal x squared and du equals 2x dx. Oh, it works perfect. So in for x squared, I'm going to put a u in there. So I've got the integration of e to the u. And then in for 2x dx, it's all going to go bye-bye, and I'm going to put a du in there. Oh, another great rule. Well, I'll do this so you can see some of it still. Another great rule. The derivative of what equals e to the u? Well, the derivative of e to the u is e to the u. It's itself. So now I end up with e to the u. There are no bounds, so I need to put plus c. Okay? This is still tan negative 1 of y plus c. One thing on the right-hand side. There are no bounds. I need an expression, so I got to put my x back in. I got to put this back in for u. So when everything is all said and done, I have tan negative 1 of y plus c equals e to the x squared goes back in plus c. Okay? Now, all right, I want to get my y alone, which means I'm going to get rid of this constant. Remember, this is like a constant 1 and constant 2. They are not the same numbers. So when I subtract this, boom, I got tan negative 1 of y equals e to the x squared plus some constant c. You can call that c3 if you want. You know, I don't. It's just a constant at this point. All right? Now, I always have a lot of kids tell me, how am I supposed to get this y out? Okay, let's think opposite math. Okay, the opposite of addition is subtraction, right? When I got to do opposite math to solve for a variable, and vice versa. These are opposites. The opposite of multiplication is division. Okay, these are opposites, right? The opposite of squaring is square rooting, right? Yeah, it is. It is. Okay, so what's the opposite of inverse sine? Well, regular sine. These are opposite operations. They would cancel each other out. Meaning, if I have tan negative 1 here, what do I do to this side to get rid of the tan negative 1? I do a regular tan. It's crazy, right? This cancels with this. So I end up with y. What I do to one side, I have to do to the other. And this is a great problem for a multitude of reasons, okay? For a multitude of First, okay? First, when we get our separable differential equations, which is what we're working on, that's the content we're working on currently, the first thing you should notice is I need to use a trig rule, especially for something that doesn't have trig there. It's not like I'm trying to figure out, okay, well, I'm integrating cosine. What do I take the derivative of? Well, I know sine would give me the derivative of cosine. No, trig isn't even in here. You got to remember that's an inverse function, first thing, okay? Next, you've got to be able to identify u sub. That's great. After that, the algebra brings in something that we really don't use that often, okay? My opposite math that I'm using is inverse trig to regular trig. That's not something we do a lot at all. So this problem is really, really, really it's a really great problem to do, okay? I think we're done. Let me see, we're still going. 27 minutes. Yeah, we're done. Okay, the rest of this packet are problems for you to try on your own. And hey, Godspeed. Good luck. Leave me a comment. Okay, like this video, ring that bell, share it. I will answer any comments. Watch a few more videos. I am not doing a review unit for Unit 7 because last year's pre-calc class didn't get through Unit 7. I will be teaching them Unit 7 just as I would have taught it to them last year. We did not have enough time to get to it. So Unit 7 is going to deal mostly, and I think it's only like 4 or 5 lessons, somewhere around there, of area between two curves, volume for rotation, making discs and washers, and I think that's it. So, hey, it has been real. Maybe I'll make some Unit 7 videos. I have older ones, but now I'm older. I'm wiser. I've been teaching this for a little bit longer. Maybe I could make some newer videos for that. Who knows? Or maybe work on some Algebra 2 videos, Algebra 2 regions. Hey, it's been real. I'll see you again. We're going to have some test review videos coming up in the not so far future. So, hey, like it, share it, do whatever. I'm going to miss you, but I'll see you soon. Take care.